Hello everyone, so welcome back to the fourth lecture of this week. So we are discussing the transformer architecture. So we have done the major work already. So we described what is the encoder of the transformer like. Now in this lecture we will focus on the decoder part. Right? We will reuse the components that we have already learned, and we will see what extra is needed to add a transformer decoder so that we can get an encoder decoder model. And then we will also briefly tell that if you just want to use transformer as a language model, what you will need to do, right. So if we do these two, generally it completes the discussion of transformer as an architecture like RNNs, right. So like we could do with RNNs, we could encode sequences, we could do language modeling, we could do encoder decoder. So we could do the same with transformers, right. So we will discuss what is decoder and what is the language modeling paradigm with transformers. Okay. So this is a picture. So till the last lecture we were only seeing mainly the encoder part, right, and we had seen one encoder. The same thing is applied at multiple encoders. You can have 6 encoders, 12 encoders and so on. So but the same blocks repeat, right. And then finally you get some representation at the end of all the final encoder, the final output. Now what happens in the decoder? So this is where you are seeing the first decoder, and as like encoder, the same block will repeat for decoder 2, decoder 3, decoder 4 and so on. Now what happens in decoder? If you see this block, I am still feeding the words, right, but I have to generate, so it's not clear what words I will feed. So let's keep that in hold, but we will feed something here. I'll apply self attention, okay. I'll do add-in normalization, plus I have an extra thing, right, because when I'm generating, I should be able to make use of what is my representation, right. Remember with RNNs, we had to make use of the encoder representation while generating. So there should be some way in which the decoder will pay attention to the encoder states, and this is the encoder decoder attention. We also call it cross attention. So the other thing was self attention, that is within the encoder itself, and this is also self attention, this is within the decoder itself. But this part is cross attention because decoder is attending to encoder now while generating the representation, and this is an extra thing, right. And then you have the add-in normalize, feed forward, add-in normalize. This is something we have already learned. You have multiple decoders. Finally, because you want to generate, you should be able to project it via linear layer to the vocabulary space and do softmax and decode, right. Depending on whether you are training just computer loss or at inference time, you can decode, and we discussed multiple decoding paradigms in the last week with RNNs. So you could use the same decoding paradigms with transformers as well. So okay, so this is the whole picture. So let us see what is new in the case of transformer decoder. Okay, so this was like in a nutshell, this is encoder, and this is what you have in the decoder. So self attention, and this is the extra thing, and feed forward. But even in self attention with decoder, there is some slight change compared to what you have in the encoder, and this is why it is called a masked self attention, right. So what happens in the decoder? So while you are generating tokens, you cannot access the future tokens, right. That's one difference with the encoding and decoding side. So when you encode, you have the entire sequence at your hand. So you are trying to translate a sentence, I went to market, and in the decoder you want to generate मैं बाजार जाता हूँ in Hindi. So while you are decoding, say you start with the start token, while you are decoding for the word, say you have done these two, you are decoding for the word bazaar, I can't put attention on the future tokens. I can't put attention on jata and home because they are not even generated. So, I have to put attention on whatever has been generated till now, right. So, this is where this masking comes into play, right. So, what is the masking idea? So, I would do the same operation that I was doing, like I will do q times, I will do q for the entire sequence, right. Now, this is again assuming that you are doing the training. So, at training time, I have the entire sequence available to me, right. So, I have the entire sequence available to me, including the future tokens that I am going to generate. So, if you actually take query keys from all of the future tokens, you already are getting leaked information from the future, right. You already know what are the tokens that are coming next, you get their keys, it will become much easier for you, or it will not make sense in practical setting, right. If you know what you have to generate, then what are you really generating? So, you want to mask those. So, you still want to do things in parallel, right. You do not want to do one by one, you still want to do things in parallel. So, you have all the queries for all the words, but while attending, you will only attend to the previous keys, not to the future tokens, and that is implemented through masking. The masking idea is that, so this upper triangle is set to minus infinity. So, you add something minus infinity to something, and then you do e to the power minus infinity, that will come out to be 0. See, you did not do it at 0. Why? Because e to the power 0 is still something, right. It will still contribute. So, I want to make it completely 0. So, I add minus infinity, then it becomes really 0 after taking softmax, right. So, this is masking. You put minus infinity for all the future tokens in the key, right, and that is all. So, and very important, it is needed so that you can train efficiently. You can train efficiently, you still take all the queries of all the words in the training data, I mean in the sentence that you want to generate, but you do not attend to the future tokens, right. So, this is only helpful for efficient training. So, if you did not have any worry about efficiency, right, what you would have done, like you were doing in other models like RNN, you would start from start token, and I will generate I, and I can anyway not attend to the future tokens because I do not have those, right. And then I generate something max probability token, I do teacher forcing, and I put I back, and next I generate its entire path, right. But there you would anyway not have attended to future tokens. So, this you could do, but this will be very inefficient, right. The important thing about RNNs, the transform model, is the efficiency that they bring in. Now, you can do things in parallel because there is no direct connection between the two hidden states, and you all anyway know what is the next word that you have to generate. So, why do not you give the entire sequence, but you do not do any cheating. So, you do not put weight to the keys of the future token, and that is implemented through this masking, right. So, this is important at training time to maintain efficiency, so that you can still do computations in parallel, right. You still want to compute the entire matrix, all the words in the sequence, right, not one by one autoregressively. At decoding, at generation time, you will have to do one by, I mean at inference time you will have to do one by one, but at least at the training time you can be efficient and do not by not attending to the future token. So, this is a very important concept that helps you do maintain efficiency at training time. Okay. So, this is how the mass self attention looks like for decoder. So, ith position. So, let us say 0th position will attend to the 0th position only. First position will attend to 0 position and 1 position only, and not to 2, 3, 4. Second position will attend to 0, 1 and 2, not to 3 and 4. Third will attend to up to 3, not to 4, and 4 will attend to all the tokens in the sequence. Right. And this is a trick in which you can do training in parallel for all words in the sequence. Okay. Right. So, this is one thing in the decoder. So, you have attention, but it is called masked self attention. So, that is one change we saw. What is the other thing we saw? See, once you have done this masked self attention, you would be able to get some decoder output, I mean self attention output. So, what is done next? So before you do add-in normalization, you do encoder decoder attention. So this is what you have the decoder state at the current point of time. Now you want to attend to the encoder states. So let's say these are the 3 encoder representation corresponding to 3 input words. Right. You want to attend to this final representation. This is the final representation that you got from the encoder. Now how would you attend? How would the decoder attend to the encoder? Right. Remember the attention idea? That's very generic. So if the decoder, let's say the first token has to attend to all these states, where should the query come from? Right. The query should come from the decoder. So I should be able to get the query from here, and the key and value should come from the encoders. So that's why so K1 V1, K2 V2, and K3 V3, key and value will come from there. So that means I need another matrix for this cross attention. So I need WK, WV, and WQ. I need these 3 matrices. Again, I will have multiple attention heads, H attention heads. So I will have roughly the same kind of mechanism, but now in a cross attention manner. Okay. So I'll again have WQ, WK, WV, and for all these for all the H attention heads, right? And I'll have WO finally to project the concatenation of self attention output to the model dimension, right? So that's what I will have, right? So I need encoder decoder attention layer, so which would help the decoder to focus on the encoder states. Okay. So yeah. So then what will happen? So once you get the decoder output finally, right, I'll apply, suppose I get an output, let's say I got an output I. By teacher forcing, I feed it back, right. So let's say you are doing inference time, right, or at training time. This is the ground truth token. So you feed it back. So this is where I is fed back, and you add the positional encoding. So positional encoding you have to also do at the decoder time, and this whole thing will go through the entire decoder, will generate some representation, the model dimension. You will apply linear layer and softmax to project it to vocabulary dimension, and from there you either select a word or compute your loss, the cross entropy loss, right. So that means everything else is very similar to what you had in the RNN. So once you know how to get this final representation, at some point you just had to project it to get a distribution, and then from distribution what you do will depend on whether you are doing training or you are doing inference. So again at training time, you only thing you do is to compute loss. So in this case, because suppose you are doing translation, loss will be cross entropy loss. So typically cross entropy loss, right, you accumulate over the entire ground truth sequence. At an inference time, if you are using, you will simply have a distribution, you will learn how to decode. So you can apply any decoding algorithm. Okay, so that's one thing that you should always keep in mind, that once you have the distribution, what you do depends on whether you are training or you are doing inference at this point of time. Okay. So again, just a quick recap of what happens in the linear softmax layer. So you have the decoder stack output, the model dimension, right, at the final decoder layer. Now you project it to the vocabulary space through a linear layer, so entire vocabulary. So you have D cross V matrix to project it to the vocabulary space, and then you want to compute your loss or the probability. So you apply softmax. So you get log probabilities, right. So you get the probabilities, and from there you can do argmax or something, that depending on your decoding logic, right. Now this is all is done by the final layer, and this is very similar to RNN decoder, okay, or RNN language model, you can say. Okay. So you can try this problem to get more idea on how this decoder multi-head attention works. Okay. So in this problem, what is being given? So suppose you are training your transformer decoder, okay, and this is the ground truth. How are you? That means you have to generate it, and you have to compute your loss, right. So this is entirely given to you, the entire sequence. So you will start from the start token, and you have to feed how are you and the ground truth is also known. So, at the end of the decoder you should generate how, are, you, end of sentence. So, this is the input to the decoder and this is the output that you want, right. In between you will do the mask self attention, encoder decoder attention, feed forward layer, whatever, right, and finally linear layer, but this is the input and output and that is how you will compute the loss. Now, what is being told, you should compute the multi-head attention output for the word R. Okay, so the focus is the word R. Okay, fine, and we are just saying you ignore this. So, for just for now ignore that there was a start of sentence token, they would be, but let us say you ignore it. So, that means right now in the sequence I have how are you that I have fed for the training and these are the ground truth tokens for are you end of S. Okay. Now, what do I need to do the attention everything? First of all, I need to know what are the encodings of these, right. You also ignore the position encoding for now. So, what are the encodings for how? So, it is given that remember this concept of in vector and out vector that we talked about in the case of word embeddings. So, we are just alluding to that. Let us say for each of these words, some words you are given in vector and out vector. So, what you do, you take the concatenation of in and out vector to get the embedding for each word. So, what is the embedding for how? This is -1, -1, 1, 1, 4 dimension embedding. What is the embedding for R? 1, 1, -1, -1. What is the embedding for U? That is -1, 2, 1, -2. So, I have the embedding for all these words. Good. So, that is start. What else is given? So, what is the projection to query key and value to compute the multi-head attention? What is the query key and value? So, it is given that the first and third dimension of the input define your query. So, what is query for how? Oh, you have two attention heads. Okay, so slight change, but for both of these, so query will be the same in this case. So, query will be -1, 1 for how, and the key will be second and fourth. So, again -1, 1. So, like that for each word you have the 4 dimension embedding, first and third define your query, second and fourth define your key, just for this example, and this happens for head first head and second head. So, what is difference across the two heads is the value. So, for the first attention head the value is the in vector. So, V for how is -1, -1, right, for the first attention head. Second attention head, that is 1, 1. Okay. So, that is the only change. Query key remains the same, value changes across the attention heads. And you have to tell what is the output for the multi-head self attention block for R. What is the output for R? Right? We are not doing encoder decoder attention, just self attention. So, what is the output for R? Okay. So, let us try. So, these are the what I have extracted from that table. So, these are the embeddings I need. So, how is -1, -1, 1, 1. So, you see query and key are same for both the attention heads. So, I can just compute the dot product once, right. So, query for how is -1, 1 and key for how is -1, 1. Query for R is 1, -1 and key for R is again 1, -1, right. Now, I have to do attention output for R. So, should I consider U? Right, that is the one trick. So, now I am doing decoder, right. So, decoder R cannot attend to U. So, even if it is known to me, I would put -infinity in this in its attention. So, it is as if I should not even use the query key for U. So, I only need the query for R and keys for how and R, right. That is all I need. So, I will now compute what is the dot product of QR dot K how, that is -1 and -1, -2, but I have to also do scaling. Dimension is 2, so divide by square root 2. Second, R and R, query and key, so 1 plus 1, 2 by square root of 2. So, this is minus square root of 2 and square root of 2, I have to do softmax of that. So, this I calculated for you and this comes out to be 0.06, 0.94. You can verify this. Okay. So, I have this dot product attention vector. Now, I have to do multi-head attention, right. So, for the first attention head 1, my value is, so value of two words how and r. So, v of how is -1, -1, v of r is 1, 1. So, what will be my final output? I will say okay, 0.06 weightage to how and 0.94 weightage to r. So, for the first attention head, I call it G1, the output will be, so I put 0.06 on this, so minus 0.06 plus 0.94 onto r. So, this comes out to 0.88, again same thing, so 0.88 is the first attention head output. Same thing I do for the second attention head. For the second attention head, I have v of how is 1, 1 and v of r is -1, -1, right. And now I apply this, I multiply with this, so I will get 0.06 minus 0.94, so minus 0.88, and second dimension is the same. This is second attention head output, right. And I have to concatenate this. So, my final output before applying to double knot matrix is 0.88, 0.88, minus 0.88, minus 0.88, and then I will apply double knot matrix to put it back to the model dimension. Okay. So, this is what I do, right, for multi-head attention, and I will do exactly the similar thing for the encoder decoder attention, but that time the key and the value will come from the encoder final representation, and query will come just from the word in the decoder that I am trying to represent. Okay. You should do that on paper yourself and verify that you are getting this similar output. Now, as I said, we will also talk about how do you use transformers as language model, and you remember the connection between language model and decoder. They work very, very similarly. Language modeling also, given the previous words in the sequence, you generate just the next token, and decoder also you do the same thing. You have an additional encoder context, but other than that you just generate one token at a time, right. So, what happens in the transformers if you are just using as a language model? That means there is no encoder, right. First important thing is there is no encoder. So, you are feeding some words W1 to Wn, and you want to generate what is the next word in the sequence. So, you will use entire machinery for transformers to represent them at the lth layer of the transformer, and then from there you will project it back to the vocabulary dimension, right. And this you will do softmax. You first set logits, the real values, you do softmax, and you get the probabilities, 1 cross v dimension probabilities, right. And from there you can compute your loss in training and decode the next word in the inference time. So, what is typically done, because see what you will do, so you will embed the words, and embedding is vocabulary, projecting vocabulary to d dimension. This is what you do in embedding, and here what you are doing, you are projecting d back to vocabulary, right. So, this is why this is also called unembedding layer. So, unembedding means you are now using the latent representation, putting it back to the vocabulary dimension, right. So, that is just an embedding, and one interesting that is done is that you can tie the weights. So, you can tie the embedding weights and unembedding weights, okay. You can tie the weights, so that the weights are learned, so that they can project from vocabulary to the d dimension at the input time, and they can project it back from the d dimension, the latent representation, to the vocabulary space, okay. So, this is why it is called the unembedding layer, because this linear layer projects from 1 cross t shape to the logit vector that is 1 cross v shape, right. And this is tied to the embedding, right. So, weight tying is a nice idea by which you can say these two weights can be shared, and I do not have to make multiple copies of the same weight, and they are, because they are also doing very similar functionality. This is going from vocabulary to the latent representation, and this is going latent representation to the vocabulary. So, there should be some connection between the two, right. So, that is why we just can tie the weights, okay. So, that is what is your language modeling head. So, you have given a sequence and you compute the representation and you use the representation to the final d-dimension representation through this unending layer to project and get the word probability. So, you get one score for each of the v possible words in the vocabulary, okay, and softmax will turn into the probabilities again of shape 1 cross v. Right. So, you have this is the output for the lth layer d dimension and you have this d cross v that will project it back to v vocabulary space. So, this gets you 1 cross v. Now, next you apply softmax and this gives you the probabilities, right, and that is what you do at the language modeling in the case of transformers. Okay. So, just to tell the entire sequence again. So, you are feeding the encoding of the words, you are adding the position encodings. So, you have the position encoding also. Then you are going through the entire layer normalization, attention, feed forward, you get the output for the first layer, this becomes the input for the second layer and entire machinery you get the output. Finally, you have the output by doing this for L layers, you get the output for the Lth layer. So, this is exactly same as what you did at the encoder, right. Of course, you will do mask attention because you will not attend to the future tokens. You may have entire sequence at your disposal, but you will not attend to the future tokens. So, you simply do mask self attention, but there is no encoder decoder attention. That is there for language modeling head, but there is no encoder decoder attention because there is nothing like encoder here. You are only decoding, you are only generating the next token, right. So, there is no encoder in this language modeling, and this you will use the as a language modeling head, you will convert this d dimension back to vocabulary and you can sample a token, right, to generate at the next position. Okay. And this is what is something that we have discussed multiple times, that how do you take a latent representation, call it the sentence representation till at this point and convert it to the vocabulary space. Okay. Now, we can quickly see what will be the number of parameters when we use transformers and encoder decoder. So, encoder we simply worked out is 12d square per layer times number of layers. Now, what will happen in decoder? So, decoder, the only change that happens is that you are masking, but masking does not introduce any new parameter. This is just simply you put minus infinity to the future tokens, there is no additional parameter. So, no additional parameters there, but you have encoder decoder attention. So, this is exactly like self attention, you need exactly same number of parameters, you need to compute your query key and value matrices, get the self attention output for all the attention heads, project it back to the d dimension to W naught. So, it will have the same parameters as self attention. So, that means you have this 4d square additional parameters. So, per layer of a decoder you will have 12d square plus 4d square. So, 16d square parameters, right, so that you can attend to the encoder. So, that means if you have L layers of encoder, L layers of decoder, you need 12d square times L number of layer for encoder plus 16d square times number of layers for decoder. Now, these does not include the embedding parameters and the unembedding. So, you may tie them, you may decide not to tie them. So, you will have plus some parameters for going from vocabulary to dimension. So, v cross d for embedding, and that you can multiply by 1 or 2. I mean, I should say 1 multiply by 2 optionally if you do not tie. If you do not tie the parameters, right. If you do not use the embedding and embedding layer as weight tied, you have to multiply by 2 because you are giving at the input and also you are generating your vocabulary from there. Otherwise, if you are tying, this 2 will go away. So, these are all the parameters typically that you have in the encoder decoder. Now, similarly, what would happen if I am using only decoder only transformer, and these are what are most prominent recently. So, recently people have moved towards decoder only transformers. We will discuss more about that. But what are the number of parameters? So in decoder only parameter, again let's forget about vocabulary. So you have L layers, and each layer has mask self attention. There is no encoder decoder attention feed forward layer. So again you have same as encoder 12D square parameters, right? So that means if you are using only decoder only transformer, this has exactly the same number of parameters as you have in the encoder only transformer. So this is 12D square into L number of layers, and plus you have another parameters for the vocabulary, vocab times model dimension, and again crossed into 2 if you are not tying the weights. So decoder only models have exactly same parameters as the encoder only model, but if you are using encoder decoder models, then you have much more parameters. You have something like 12D square plus 16D square per layer that you are having in encoder decoder, right? So this is more than double the parameters. Okay, and that may be one of the consideration why decoder only transformer models are most prevalent recently. So we'll discuss further. So this completes our discussion on decoder. So we'll discuss further in the next lecture on some other variations of transformer that are important. You can go through our chapter 9 to discuss whatever we have covered till now. Thank you.